Hello, thanks for joining. My name is Mohammad Farzanullah and I am a master's student at Medical University. Today I will be presenting a paper which has been accepted at WCNC 2022 titled as Deep Reinforcement Learning for Joint User Association and Resource Allocation in Factory Automation. So this is the outline for our presentation. We will first start with introduction, followed by system model and problem formulation. Next, we will talk about reinforcement learning-based resource allocation. Then we will show results and we will conclude our presentation. So starting with the introduction, 5G supports three main use cases, which are enhanced mobile broadband, massive machine type communications, and ultra-reliable and low-latency communications, or URLLC. So our focus for today's presentation is enabling URLLC in industrial automation system. The previous generation of wireless technologies were unable to provide high reliability and low latency. However, the industrial automation communications requires a reliability of 0.99999 within a latency of 1 millisecond. In the future factory setting, it would consist of multiple autonomous robots, such as the automated guided vehicle, and it is observed that the devices work close to each other, due to which clusters of reliable device-to-device communications can be formed. So we consider a mobile robot scenario in industrial environments, where the robots are connected to the access points through the 5G network, and all robots require control messages. We consider a factory floor setting which consists of multiple clusters, where each cluster consists of one leader and multiple members. We divide the communication into two phases. In phase one, the APs combine the control messages of all the robots within the cluster and transmit them to the corresponding cluster leader. While in phase two, the leader relays these messages to all the members via point-to-multipoint D2D connections. For phase one, we adopt multi-agent deep reinforcement learning in a distributed manner for joint user association, channel assignment, and power allocation. Also, the agents, which are the cluster leader in this case, they only use their local channel information to make their decisions. So moving on to the system model and problem formulation, we consider a factory floor setting which consists of multiple access points and multiple clusters. We assume that there is a limited set of available subbands, and as it can be seen in the figure, the highlighted part shows the clusters, where each cluster consists of one leader and multiple members. So in phase one, each cluster leader autonomously selects the access point along with the subband and transmit power level. In phase two, the leader group casts a message to members via point-to-point, point-to-multipoint connections. So we consider both large-scale and small-scale fading in our simulation. So these are the performance metrics for phase one. So for phase one, we first calculate the SINR, and for each cluster leader, the interference occurs from the other access point to leader links, which are using the same subband. And so using this SINR, we then calculate the Shannon, we calculate the rate using the Shannon capacity formula. Moving on to phase two, similarly, we calculate the SINR, and in this case, the interference is from other leaders transmitting to their members in the same subband. And similarly, over here, we use the Shannon capacity formula to calculate the rate. So moving on to the problem formulation, each robot is required to receive the clusters control messages of size P within this time latency T. So we formulate the requirement as the probability of successful delivery of packet having size P, and it is shown in these formulas. So for our resource allocation in phase one, we need to find for each cluster leader, we need to find the serving access point, the subband, and the power level in order to maximize the packet delivery probability. For this, we use the multi-agent reinforcement learning approach. Meanwhile, for phase two, we consider a fixed key where each cluster leader transmits to its cluster member on different time frequency resources. So moving on to the reinforcement learning-based resource allocation. So in our approach, each cluster leader acts as an agent and interacts with the unknown environment. And based on the reward it receives, or the feedback it receives, it defines a strategy for user association and resource allocation. And in order to ensure collaboration, we use a common reward for all of the agents during the centralized training stage. Moreover, the testing is implemented in a distributed manner where the trained deep queue network is used to select the action. There are three main elements for any resource allocation problem, which are the state space, action space, and reward design. So for state space, we consider the measurements from the last time step, which includes the channels from the access points to the cluster leader, the interference at the agent, and the remaining payload and time. The action space consists of the combination of the access point selector, the subband, and the transmit power level. So moving forward, we use a common reward for all of the agents, which is given by the sum rate of all the cluster leaders at time t. For a given cluster leader, if it has completed the transmission, its rate is denoted as U, which is greater than the maximum rate possible. This is to indicate to the algorithm of the successful transmission of the packet. So moving forward, the reinforcement learning algorithm we use is the deep queue learning. And in reinforcement learning, the goal of the agent is to maximize the cumulative return, which is the sum of the reward at current and future time steps. Meanwhile, a policy is defined as a function that maps the state to actions. The Q value or the Q function of a state action pair gives the expected return of a state action pair with a given policy. And so the aim of the RL is to find the policy that maximizes the return at each time step. So in Q learning, if we can accurately estimate the Q values, the optimal policy would be to take the action in each state that maximizes the Q value or that maximizes the return. So basically, we use the deep Q learning, which uses a functional approximator for the Q values. And basically, it consists of a neural network that takes the state as the input and it outputs the Q value of each of the possible actions. So moving on to our training algorithm and testing strategy, we consider an episodic setting with each episode corresponding to the time limit of delivering the packet. Each episode consists of multiple time steps. At the start of each episode, the device location and large-scale fading is updated, while at each time step, the small-scale fading is updated. At each time step, each of the agent observes its local channel and takes an action. Based on this, it receives a reward and moves on to the subsequent state. This tuple of state, action, reward, state is stored in the memory and is used to train the deep queue network. Once the training phase is complete, we move on to the testing phase, where each agent uses its trained deep queue network to take actions. For phase 2, we consider a fixed scheme. So moving on to our illustrative results. So the simulation setting, we consider a square factory floor having an area of 40 by 40 meters square. Within the factory floor, there are multiple robots that move with a velocity of 1 meter per second. And each robot can move up, down, left, or right with an equal probability. Also, we assume that the robots forms clusters and the cluster moves together to perform a specific task. So to model the path loss, we use the A1 indoor scenario of winner to channel models. While to model the small scale fading, we use the Rayleigh fading to model the small scale fading. And so for performance, we use performance measure, we use the average successful payload delivery probability. So these are the simulation parameters. Some of the important ones are that there are 4 access points that are distributed within the floor. We vary the number of clusters between 2 to 8, and in each cluster there are 4 members. We discretize the transmit power of the access point into 4 levels, that is 30, 25, 20, and minus 100 dBm, where minus 100 dBm corresponds to no transmission. And the latency T is set as 1 millisecond, and the robot payload size is varied from 20 to 100 bytes. So moving on to the results, the first graph, this shows the training performance, and this basically shows the reward at each of the training episode. As it can be seen that the reward is increasing during the training phase, which shows that our algorithm is learning. Moving forward, this graph shows the performance with respect to the payload size. And so over here, we compare the performance with exhaustive search and random allocation algorithms. For both exhaustive search and random allocation, we assume that the cluster leader connects to the access point that is closest in the distance to it. And in this case, we set the number of clusters to 4, and during the testing stage, we varied the payload size. And it can be seen that our RL algorithm performs close to that of the exhaustive search algorithm. And basically, it shows that our algorithm is able to perform well for a varying number of varying size of the packets. Moving forward, here we compare our performance with respect to the number of clusters. Here we set the packet size as 40 bytes and we vary the number of clusters. And over here, it can be seen that the RL algorithm performs close to exhaustive search for all of the number of clusters, which shows that even for a large number or a greater number of clusters, our algorithm still gives good performance. So moving on to the conclusion, we developed a two-phase communication scheme for mobile robot scenario in the factory automation system. And this was based on the fact that the robots and the factory floor, they work in close proximity and they can form multiple clusters for reliable D2D communications. So in phase 1, the access point associated with the cluster leader combines the message from the cluster and transmits them to the cluster leader. While in phase 2, the cluster leader relays and broadcasts this message to the cluster members. So for the communication in phase 1, we use multi-agent reinforcement learning as a distributed algorithm for joint user association, channel assignment, and power allocation. And the agents basically use only the local channel information to find the resource allocation. And it was proven that the proposed approach provided reliability close to that of the exhaustive search algorithm. So these are the references. And thank you for listening to the presentation.